Yeah, so the first question is, now we have two nodes and or three nodes actually, and they want to talk to each other. But how do they, in order to talk to you, I have to say, excuse me, can I talk to you? But when I say that, I am already talking to you. So we have this kind of, chicken and egg problem. Uh, so what could the solution be for that, for the hidden terminal problem? Oh, right. So I think that the short answer is that there are some solutions, and I would put that in quotes because it's not a problem that you can perfectly solve. That right, because there is no way, right? And I don't know if any of you guys have watched Star Trek, but Star Trek is before your time in some ways. Not just the new Star Trek stuff, uh, but the whole principle of every kind of episode in Star Trek, especially in the uh, one where Captain Picard is there, in that one, is that there is a game and you cannot win the game based on the rules of the game. And so then the question is, how do you solve that kind of a problem? So that's a type of a problem, right? So, and the only way you can solve that game is to not play the game. But you can't not play the game, but how do you change the rules of the game then, right? And in our case, the rules of the game are essentially the physics of electromagnetics, and the physics of the energy basically radiating out. Okay, so that's one question. What other questions are there?
When you're sort of sending packets over a network, how does a device know that it's like that the target of the message?
How does the device know? Okay, how does the device know? Yeah, because like I mentioned before, like next to my house in Center City, Philadelphia, there are at least 42 wireless networks. That just means that my phone and my laptop can listen to all those packets running across those 42 networks. If we are in a classroom and there are 40 students in our classroom, then and one is supposed to receive that message. How do you know that? Same thing with your cell phone, right? Your cell phone is one among hundreds or thousands of cell phones. Say you go for a concert, right? Post COVID, you finally are able to go for some kind of rock concert or music concert, and there are 80,000 people in that concert. And how does it know that your phone should receive that message? So who can tell me what that would be like now? Like that there is a message coming, and the message is just for Kate, right? So how do we know that?
Is that like what IP addresses are?
Yeah, but what are IP addresses, right?
It's like a long numeric, like.
Yeah, but what is that, right? I gave you the answer by saying that this message is for Kate.
I guess the beginning of the message, it mentioned a lecture about there's like a header to every message, and I guess that.
Yeah. So we'll look at that too, right? I think the question over there is, so how do we get this message across to each person among many other people, right? So we have to have some way of tagging that person, some way of labeling that node, right? So how do we get that across? So that's a good question.
Question I had, I had two questions. One relates to that. Why isn't it easier to like steal other people's messages? Like if you know the person whose IP address you want to steal, messages going to them, like, is it hard to tap stuff that they're I don't know. If it's going to everyone, then.
So say there's a message, there's a message for Gregory, and then we want to tap that, right?
And I wanted to steal it or something. Yeah. Why isn't it like, why it's obviously trivial to do. So why?
Isn't that a man-in-the-middle attack where you can route all the traffic through a computer and then you just listen in? But I think these days everything is encrypted. So you have a public and private key, and so and then you give out a public key, and then only you have the private key. So only you can decrypt messages for you. So
That
that
would
way,
end-
even if you're listening on the middle, you can get all those packets, but like you won't be able to make any sense of them because they're all encrypted.
Is that what end-to-end encryption is? Like everyone has a private key, so like it's
Yeah. But I think public key, private key. That's a technique, right? So that is one technique for being able to have, so you want to have message integrity, right? So one is integrity. That means you got the message that I intended you to get, right? So you didn't get like a garbled message. So that's where we have things like parity check, and we have checksums. But then the second is authentication, right? So that means, can you join AirPenNet or not? Do you have, so then you need some way of saying that, I am, I am who I am, and I'm not somebody else. And how do you demonstrate that, right? How do you actually show that? So for authentication, you need some kind of a way to have some. So there are all these words of like credentials, right? So you need to have credentials, and credentials are basically just saying that, they have given you this kind of certificate, and you have that certificate, and you're registered in their system, and they can actually look you up in their system, and then therefore, so there is basically like a certificate server that you basically say, hey, you gave me this certificate, and then it says, yeah, I did give you that certificate, and that certificate is encoded in a way that only they can decode. And then they say, yeah, we did give you the certificate, and you have the right certificate, and it basically is matching your credentials like that, right? So that's one way to say. But then the next level is to say, okay, well, how do we prevent, any kind of eavesdropping or any kind of sniffing device from capturing that, right? So yeah, even I want some lunch. And then so then the question there is, yeah, like, so man in the middle is a type of an attack like that, right? So, and there are all these names for the types of attacks, but you have to sort of say, well, what is this? What is this man in the middle? Like, so we don't want to just throw the words of man in the middle, public key encryption. Those are kind of ways of identifying a type of the problem, right? But what is this problem? The problem is that I want to send you data without this data, being read by anybody else, right? So how can I actually achieve that? So encryption is one approach to doing that, right? So where you're like now taking the bits that you actually generated. So say you basically have 1 2 3 4 5 6 7 8 9 10, and then you are garbling that in some way, right? You are passing that through some function, and the only way to undo that function is on the other end of the network, right? So they have some kind of a asymmetric way that, that I can send you garble messages and you can ungarble it, because you have some way to ungarble it, and only you can ungarble that, right? And but nobody else can. So how do you do that? And so then there are sort of challenges with that, right? So but that means that we both share a secret. That means I've told you that, look, I'm going to garble messages like this, and in order for you to ungarble it, all you need to do is just add a 1 to every byte that you get. It's a stupidest scheme because it's so easy to guess like that, but or it's a fixed pattern. But then that secret is something I told you, right? And then now you have that secret, and then you can just apply that secret. So then in terms of the security protocols, they have to figure out a way, how do we tell the secret to you? Because again, it's kind of like this communication between these 2-3 nodes, that they need to have a secret, but you need to communicate with that secret. And how do I get that secret across to you? Because I have to then use the same communication channel, and then so anybody can hear that secret. If they hear that secret, then they can continue, right? So that is again a game that you need to figure out, how do I get across that? And now like Penn has instituted like this, two-factor authentication, because let's say somebody's able to steal your password, but well, they need to steal your password and they need to have your phone to get a SMS. Sometimes it's really silly. They even apply this for the library. I just want to check out a book, and I need to do that. But well, that's the level of the inconvenience you have to go through. But to make sure that we can actually, even if there is a leak in the network, in terms of one way. So then you need to have multiple factors of authentication for doing that, right? So we'll go through where this encryption actually, where does it reside? We won't go through like what is the particular functions for doing encryption. That you would have to go through and listen to, these are kind of basic problems. They are solved to a pretty good extent, and there are sort of newer and harder problems in terms of just getting messages across. But we'll look at the packet types, right? We'll look at the packet types, which can then identify who's the sender, who's the receiver, who are the intermediate parties, and then who should be able to only read. Everybody can read a part of the whole packet that they're getting, because they need to know, oh, this packet is for me or not for me. If it is not for me, should I forward it to someone? If I'm a router, should I just drop it if I'm just a regular node, right? So, and then there are consequences, right? Consequences of living in, so like when we are in class, right? Then 40 of us are in the same room. And let's say one person is downloading some gigantic, 30 gigs of some BitTorrent during that, right? And then other people, usually what people do in their class, they just have their laptop open. They don't even use their laptop, but they have it open because otherwise they got to pay attention to what the instructor is saying in an undivided manner. And today we can't do that, right? You got to watch TV, you got to watch TV, play a game at the same time, and message on your phone, and have like all three screens open at the same time, because our minds just need to be like overly engaged. And that's how we are conditioned at this stage, right? So, but what's happening to that laptop that is just sitting there, and all our phones that are just sitting there, while this one person is downloading 30 GB? 30 GB of packets are coming into that room, right? They're coming into that access point in, that the 4031 B over there, of 401B, 401B classroom. So 30 GB of packets are coming in, and let's say your laptop is just sitting open, or your phone is just sitting on the desk or in your backpack or in your pocket. That phone is receiving all the 30 GB of those messages. It's not receiving the full packet, like in that sense, but it is, as soon as it is getting the packet, is looking at the packet and saying, is this for me or not? But 30 GB, let's say that 30 GB is broken down into like 1 million packets, for example, or let's say 100,000 packets. So 100,000 packets are coming to your phone just because someone in the room is downloading the gigantic file, and your phone's battery is just draining way faster than normal, because your devices, all of these wireless devices, they live in a broadcast environment. They live in a broadcast world. That means it's not like I got to like say, hey Matt, wake up, this is for you, right? I mean, the best way to wake up someone is to just tell them their name, because we are all like programmed to wake up when our name is said. And that's how we are conditioned from childhood, right? Or even like your pet name at home. If somebody says your pet name at home, you would wake up much faster than if somebody said, hey dude, wake up, man. And then you're like, yeah, it's okay. Because then you don't get triggered that way. So how do you get triggered? So every device is looking for, is this for me? Is this for me? And they do not know a priori. So there is no way to actually say, here is a wire that is just connected to you. And whenever you, like, that's like serial communication, right? It's just between two parties. Every message is for the other party. Every message received is from the other party. And that's it. It's just two of us in the whole world. And so there I'm going to wake up and I know that that message is for me. But in the broadcast world, you're waking up for every message, right? So that's just a little segue to just give you the context, right? That we are in a broadcast world now, and we need to figure out how to address this packet to us, and how do we address, and how do we make sure that nobody else reads the rest of the packet. So basically, the packet comes with a header, and the header now has to say, well, who is this packet for? So I'll pause at this point because we will go through that, right? Any other questions that are there? So far, there were two questions, right? One is, how is this hidden terminal problem solved? We'll look at that. And the second question is, how do we know this message is for me? And how do I make sure this message is not read by anybody else? Any other questions you guys have? Okay, so let's get started with that, with these two questions, and then so first we'll look at, now in this broadcast environment, the simplest way to communicate would be to just say, okay, I have a message for somebody else, and I just send the message, right? So if I just send the message without, like, say, making an appointment, right? So making an appointment with someone, or just telling them that, look, I will talk to you every Tuesday and Thursday from noon to 1:20. That's an appointment. And that means that you have to be synchronized to the same time zone, the same clock, and so do I have to be. And there is some cost of doing that, right? To be synchronized like that, right? So if, for example, if I just had my, my analog watch like this, or my daughter's analog watch, I should say, then this watch will lose a few minutes every, month or two. And so I would lose synchronization. Therefore, I have to have, like a good phone or a good laptop to maintain that synchronization. All our laptops get synchronization. Like an Apple laptop will usually connect to an Apple time server. And that every time you open your laptop, it will go and talk to the time server and say, hey, what time is it? And then it'll say, okay, well, you are located right now in the East Coast zone, or you're located right now in Istanbul, because we were able to see which network you're connected to. And so it'll update the time to, the Turkish time, for example, right? But synchronization is very expensive. And and it also requires a setup. That means we also have to be synchronized before we get started to communicate. We have to do that, right? So when networks started in the beginning, they were like, wait, we are not going to set up and synchronize the whole world, because that's why cell phone networks are so expensive, right? I mean, in the US, they are ridiculously expensive compared to other countries. That's just because of monopolies. But they're expensive because they need to set up towers, and each of the towers need to, tile over the entire landscape, and they need to service, like, say, so many people more in downtown Philadelphia or in Manhattan than, say, somewhere like, Louisville, Kentucky, or somewhere like that, right? So they have to put up that infrastructure. That infrastructure is also providing a way to say, okay, now we're going to talk to you, now to you, to you. So they have a very, they have some way of organizing the communication. So a way in which the communication is not organized is called random access. And random access basically just says that, hey, this is a party. When you go to like a house party, everybody is talking. There's a lot of background noise, and you are talking to some other friend, or you see this girl or guy, and you're like, you want to talk to them, and you're like, and then you start talking to them, and they were like, say what, and then they keep like trying to figure out what you're trying to say, because there's so much noise in the background, and you want to get a message across. Because it's random access, many people are talking, right? So let's look at what random access looks like now in the wireless world, right? So the simplest way is, I have a message to send, and I just send it. I don't care if people are talking, if people are not talking, I just send it, right? So that's called Aloha. And Aloha is a protocol that came around 1972, 1973 by this professor in, guess where, University of Hawaii, right? And what he wanted to do was basically connect the different, I think he had different different sensors. It was basically, he wanted to send a message from the telescope down to a computer where he was, and figure out how to get that message across. And it was up on a hill, and there was no way he could lay out a wire for that easily. And so then he said, oh, well, why don't I send this message across? And then he's like, how do I get this message across from different telescopes back to me? And so he said, well, if you have a message, just send it. Let's see what happens, right? So say if I have a message, and this is my message over here, that I'm sending this message at time t0, and I send it across. If it gets to you, great. But what will prevent it from getting to you is that, well, somebody else could be sending a message at the same time or just before me, and it overlaps with me. And somebody could be sending a message in the middle of me sending a message. They could also just start sending that. And then that results in a collision. And so he said, look, I just want to get, a couple of messages across. The network is not that busy that so many overlaps happen. And when overlaps happen, then the messages basically just, they have a collision and, they get garbled, right? So, but the system is very simple. That is no synchronization needed. If you have a message, send it. So what's the problem here, right? The problem is that, I want to send this message, but there is a packet that is, overlapping before me. So even before I started sending the message, it was a bad time to send this message. It's kind of like somebody's talking to you and then in mid-sentence, you're like, that's exactly what I meant. And then you don't even listen to the rest of what they're saying. And you just, and then that person is talking and you're talking at the same time. And the third person says, okay, guys, I can't understand what's happening. Why don't you take turns to talk? But there is no way to take turns to talk because everybody is just, it's a very impolite world over here. You can just talk when you want to talk with that, right? So this happens, so when this happens, then we have a collision because there could be collision with packets that were already in transmission or packets that start new transmission while we are transmitting here. Let's assume that packets are all about the same size and take about the same time for that, right? So with Aloha, you could be sending like packet 1, and this is just over time, right? So this is not like over space. So this is, I sent packet 1, great. Nobody else was talking at that time, no problem. Another node is sending packet 2, but while it's sending packet 2, about 4/5 of the way, packet 3 starts communicating. Packet 3 starts communicating, and that basically kills the receiver from receiving packet 2 or packet 3 clearly over here. So then and then the receiver basically says, okay, I didn't receive packet 3. It has to send an acknowledgement back, right? To say, hey, I did not, but if I didn't receive your packet, I don't have any acknowledgement to send. So then packet 3 is garbled. So then the sender of packet 3 has to send again and try at some random waiting time, basically say, okay, I'll just back off and I'll wait for, 33 microseconds and then I'll try again. And then and then packet 2 will pick some other random time to talk. Basically this random waiting time is spreading out the retransmission of the messages to say, well, make yourself scarce, guys, just talk after a little bit of time, and they just randomly pick a time without consulting each other. And so this is just the collision mechanism in Aloha, and that results in retransmissions with Aloha. So any questions so far with this? It's a super simple scheme, but what we need to analyze now is how good is this scheme, right? And so how would we evaluate how good this scheme is, or any kind of communication scheme? What's a way to measure a metric with that?
Like throughput?
Throughput. And so what is throughput?
Like I say it's like amount of effective data that's going through the network, like it actually sends through the network, like sort of measure like that.
Okay, so how much effective data is going across a network? Suppose I transmit to you and then I send, but the packet collides and then I retransmit. Is that twice the amount of throughput?
Wait, that's just one, because if the retransmit actually go through, like the effective amount of information that I get on my side is only like the second retransmission, right?
Yeah. So that the informal way of describing that is to say that's the good put. The good put is basically one packet, and the throughput was 2 packets, because I'm still transmitting 2 packets, but out of the 2 packets you only received 1 packet effectively. That, right? So we want to measure that. How else would we measure a network's performance? When you get a check your internet connection, right? I mean, all of you all would have tried some speed check for your internet connection. What do you see besides throughput? Okay, you get 11 megabits, you get 32 megabits per second or something like that. What else is important? So what's happening here? I'm waiting for an answer, right? But there's no, the answer is taking long to come. What does that mean?
Maybe like the ping.
Yeah, the ping. So ping is basically just a hello packet, right? So, but what you mean by ping is like the latency, right? How long is this packet taking to go from the source to the destination? Right? Suppose you have a voice call. Suppose we have this Zoom call now, right? And the Zoom call is taking 300, 400, half a second. Let's say it takes 5 seconds for my video packet to get across, but the audio packets are getting across much faster. Or let's say it takes 5 seconds delay in terms of getting, the video and the audio. For right now, it is pretty much real time, right? It just maybe like 150 milliseconds or under that, right? So it looks very real. If I move my fingers over here, you can see that, right away. And in fact, I can see that too. And this is not just my camera over here. It's going to Zoom servers and coming back to me too, right? So I can see y'all. Well, I can't see most of y'all, but in that case, we if there's a 5 second delay, then everything is lagged, and we can't have this interactive conversation, right? We can have a recording, and you can download the recording, but that anything interactive will not happen over there. And so any latency that is too large will kill that kind of application. If you're a gamer, what kind of latency are you looking for? Who of you all are gamers? And Penn students aren't gamers.
I'm not that much of a gamer anymore, but like I just tried recently Google Stadia, which is like cloud gaming.
Yeah.
So it's on your browser, and then they run all the graphics on their servers and then send it back to you. And it had pretty bad latency, so all the games were pretty unplayable. Just
Yeah,
because
yeah.
it was
See
like
that
it took like half a second or to just like when you moved your mouse for it to actually register.
Yeah, so you want some kind of latency that is like sub 30 milliseconds latency. You want your, in fact, you want to, what kind of what's a good monitor for a gamer? Like what's a good characteristic of a monitor for a gamer?
I think like high refresh rate, like 144.
Yeah, you want 144 1080p as that resolution, right? You don't want to go to 4K because you can't get 144 refresh rate then, right? Very effectively. So essentially latency is the second thing, right? So let's look at how delay and throughput are related. Okay, and we'll continue with looking at that with Aloha. So back to Aloha. Now we are in this problem over here that I want to send you a message. If there's no other traffic or very little other traffic, then I just drive like that. I mean, I just send the message. I mean, I'm just thinking about driving through Philly nowadays. There's very little traffic. So what I've seen in the last 2 weeks is that people are just like, hey, why am I at a red light when there's no other car here? So like yesterday I was teaching my kids to learn to bike, and then people are just driving through red lights through the city. They just don't give a damn, right? And because they are like, well, there's no other traffic, we can just go like that, right? Rules don't apply anymore. And of course cops were now and then were catching people because ambulances also have to go through, and it's extremely dangerous. Just people just zooming through red lights. It's almost like this is an alternate Mad Max kind of reality, right? So so when there's low traffic, then Aloha works really well because we hardly have any collisions. So let's look at now, as the traffic increases, as the number of transmitters increase, how well does it work? And surprisingly, just with very basic probability, we can actually see how that works, right? So in order for me to send you a message, it means that, and we are all in one classroom, it means that, probability that I transmit a message, say I transmit a message is a certain probability. And in the class, since I'm lecturing, I'm transmitting the messages more often than say someone else. And the people in the front and the middle of the class, they transmit messages, or they communicate or answer questions much more than the people in the tables at the back, like that, right? So there is a probability of, different nodes transmitting. And in order for me to successfully send you a message, I need to send you a message first. And at the same time, nobody should be sending a message in the time period before my time slot, right? So that means they shouldn't be sending a message anytime between T0 minus 1 and T0, assuming that these messages are the same size, because then that will cause an overlap. Of course, if they send a message exactly at T0 minus 1, then there's no overlap. But if they send a message that is, 1, or 10 nanoseconds right after that, then we have overlap, right? So there should be nobody else communicating in that time, and nobody else communicating in the slot in this time right after my message, right? So or overlapping even slightly with me. Like if it kills the last 1 bit, then it's already caused a collision, right? So well, you can say, well, with some technique I can resolve 1 bit errors, right? But here we want to see, well, that nobody else is overlapping with us. So that means nobody else is transmitting in T0 minus 1 to T0, and nobody else is transmitting in T0 to T0 plus 1. That just means that I have exclusive access to this channel. And so that means the probability of me transmitting, the probability of, let's say everybody has an equal probability of transmitting. We are a, egalitarian society now, and everyone has an equal chance to talk. And then, so probability that I transmit, this is the probability that another node does not transmit, right? So it's 1 minus that probability because it does not transmit over there, and 1 minus the probability that another node, any other node in the network does not. So since it's any other node, then we have n minus to the power of n minus 1. That means no other node is transmitting at that time, right? So 1 minus p just means you're not transmitting. What's the probability of you not transmitting, right? So if we have n nodes in the network, then basically I can resolve this into n times p times 1 minus p, and then so this basically is saying that for any of the nodes to succeed. But now if I want to see that as n, the number of nodes in the network keeps increasing and goes towards infinity, then this basically goes to the limit, and we get 1 divided by 2 to the power of e, and that's 18%. Okay, so now I'm jumping a little hoop over here, but essentially we are able to derive the probability at the limit of having a very large number of nodes. That means that the throughput of this network with a large number of nodes basically can theoretically go up to 18% of the overall network's throughput. That means if I have 100 megabits per second channel, that means if I was the only one transmitting, I could transmit at 100 megabits per second continuously. But in this case, since I have a network and we have to share it with each other, and we are all randomly participating in this network, and we cause collisions, then that basically makes us in the best case reach only 18 megabits per second, right? So, or let's say if I have 1 megabit per second, that just means I can only reach 180 kilobits per second maximum, in theoretical maximum. That means effectively I'm going to actually have a lower rate than that too, right? So I'm only effectively getting 18% of the network like that. So if we look at now, well, how do we fix this, right? So we want to make sure that we don't have an overlap with any communication that is already there, and we don't want anyone to start communicating while I'm communicating. So one way what we can do is we can start to synchronize the network and divide the network into some time slots. And we can just say, look, here are time slots, and you can only communicate start communicating at the start of a time slot. That means if these 3 nodes start to communicate at the start of this time slot, that is a collision. At the start of this time slot, there's no communication. At the start of this time slot, these 2 nodes are communicating, there's a collision. At the start of this time slot, there is this node only communicating, no collision, successful. No communication, collision, successful, successful, and so on. The point is that we do not have any overlap now between the previous time slot and the next time slot. The probability now becomes much simpler, because it's saying, well, and this is called slotted aloha, because it's just saying, well, we are all going to we're going to transmit across the network a, a, a second, or like a synchronization signal. And then you need to say, okay, well, this is the start of the slot, and I can start transmitting only at the start of this slot. And I can't transmit anytime in the middle of a slot. So we've come up with this abstraction in time of a slot. So that means that when can I have a collision? I can have a collision only if some other node perfectly transmits at the same time in the same slot that I'm transmitting, but there's no overlap between the previous slot and the next slot. So this just means that what's the probability that I want to transmit a message to you, and the probability that no other node in the network transmits at exactly the same time. So this is a smaller term than this term over here, right? So therefore, this basically becomes, now, as we have n nodes in this network, that, probability that only one out of n nodes transmits at that time. Then as we make this go to infinity, n goes to infinity, we get 0.37, right? Which is basically twice the throughput of 18%, right? So it's a little bit more than 36%, but it's just saying that theoretically, by slotting the time and saying that you can only have perfect overlaps, then you basically cannot, then you basically effectively double the throughput of that network. But what happens is when you have, like, now suppose I give you like a network that has 100 megabits per second, but you can only effectively communicate at 18 or at 32. But it also means that, like, if I'm trying to send you a message but it collides, then what happens, right? So say in this case, 1, 2, 3 are trying to send a message across the network, but it collides. None of them can get the message across. So node 1 has this packet that is sitting in its queue. Node 2 has this packet in its queue. And then now 1 and 2 start again, and they try to send this message, and it doesn't go across. And so they still have that message in the queue. Now new messages are coming into the queue. And so what this x-axis here is showing is what is the load. As the number of nodes in the network is increasing, but what we really want to look at is not just the number of nodes, but what is the number of nodes times the probability that they communicate. Then past this point here at 1.0, it just means that every packet has at least one, every node has at least one packet in its buffer. And then as the network's load goes up, it just means that now everybody's trying to communicate, but they can't get their message across, and their queue is growing. And that means I'm like, hey, I've been trying to get across to you, but I've been waiting for so long. Since then, one more packet has arrived in my queue. And so I have 1.5 packets waiting in my queue. I have 2 packets waiting in my queue. So what is going up is also the latency. So as the network throughput hits its peak, but if there are too many people trying to communicate at the same time, it's kind of like going to Trader Joe's nowadays, right? Okay, I don't go to Trader Joe's anymore. It's really ridiculous because there are so many people trying to get in, and the queue has become so long. So this is essentially the queue. Now the probability of people going to the grocery store has gone up because people are panicking, and more people are going to the grocery store. As more people go to the grocery store, the queue outside Trader Joe's keeps growing longer and longer and becomes exponentially longer now. Because inside of Trader Joe's, they can only have, let's say, only one person shop at one time, right? I don't know how many people they allow to shop at one time, but yeah, basically just avoid going to the grocery stores today. But because the queue has grown exponentially, right? So with Aloha, it's not just good news that you can get 18, it's terrible news that you can get only 18%. That means you've invested, for 100% throughput, but theoretically you can only get 18% of that. Now, what is good about Aloha is that it requires no setup. If somebody says, hey, build me a quick network, and so we can do this in a hackathon, you would do Aloha or you would not try to make something fancier. Maybe the most fancy you would get to is building slotted Aloha, because you at least want to make sure you get your messages across, and it's okay if there is some delay, right? So that's the simplest thing where no major setup is needed by the nodes. And so Aloha is good in that way. It's simple, right? But simple doesn't always mean good, right? Or at least high performance. So having a max theoretical throughput of 36, 37%, is definitely double of that. And that's what synchronization has given you as a benefit of, going from a very asynchronous network to an uncoordinated but synchronized network. So do you follow so far in this? Yes, no? Guys, we are just a small class here, so if you can turn on your cameras, that will make it much more interactive. Otherwise, I have no feedback from you, right? I mean, I can also just turn off my camera. Maybe I should do that. How about we all just turn off our cameras and then leave it at that, right? So just kidding. So this is the simplest, but now the question is, can we do better, right? I mean, 36% of this network throughput really sucks. What could we do to get to better than 36%? I mean, I don't want to invest 100% for a network and get a fiber optic link and just say, hey, your protocol sucks because, you're not going to get better than 36%. Nobody's going to buy that system because some competitor is going to come up with a better way. So what's the problem right now? How can we improve this protocol?
Is the problem that we don't know when there's going to be collisions, so we have to keep sending until we can get it through? So
Yeah,
that
so
wastes
that
a
is
lot of
part of
time.
the problem. That's a good point. So let's go from that observation, right? We don't know when. What do we know before we transmit? Like suppose you're talking to somebody, right? Before you start talking, what do you know? Like what is a way to have a polite conversation?
You take turns, so the transmitter receivers can take turns.
Yeah. And what's it, if you have many people in an audience, then you can't say, okay, now you go. We've tried that in this class, right? It just doesn't work. We
Yes.
can't take turns, but what is a general way of of polite conversation?
Like hand raising.
Yeah. So in some ways, basically just saying that, okay, I know that you finished communicating, and so I can talk. So as long as nobody else is communicating, I can talk. Sounds so common sense, but that's exactly what So then comes up this approach called carrier sense multiple access. Just has a really simple philosophy like that, right? All it's saying is uh, is listen before you transmit. And so this was work done by this professor Leonard Kleinrock from UCLA back in 1975 to 1977. So even before I was born. But his papers are just amazing. When I was a master's student, I was reading his papers and there was no simulation, no machine learning, just beautiful, derivations of coming up with how good this protocol is going to be, right? So, and this is, in fact, the protocol that is actually being used by you every day with your Wi-Fi, right? Your Wi-Fi is using this protocol all the time. Your Bluetooth is using this protocol all the time, some variation of it, right? And so most networks are using this protocol. And so in fact, Leonard Kleinrock likes to think of himself as the father of the internet. I don't think many other people agree with him, but we'll leave him at that point, right? So essentially the point here is that, CSMA is saying, let's listen before we transmit. And over here, how can I listen before I transmit? I have a packet in my queue. What I can do is I can basically listen to my antenna, and I can say, am I receiving any energy on the antenna? I don't have to be able to decode a packet from that. I just have to know how much energy is there around me. And if that energy is very high, then I know that the network around me, in terms of the electromagnetic radiation, is actually busy, right? There is some kind of signal going across that is more than just the noise floor, like that, right? And that's when, like, if you want to know how to build antennas and you want to know how to interface and detect some signal, then you would take, like, advanced analog and RF circuit design, and that would be something as a senior. It's a very good class to take. I took that when I was a senior at CMU, and I really enjoyed it, right? So, but there you're building the circuits to be able to decode, how do you receive a packet, right? Then you really understand that. Here we are understanding it at a conceptual level, but you also want to understand it at exactly in terms of the signal processing, in terms of the circuits, in terms of the information theory, and so on, right? So, and how do you actually realize that in silicon or in when you fabricate it, because you can't just use CMOS for this kind of front end analog circuits. And so that's where you would connect with other courses in that sense. So if the channel is busy, then I just say, okay, it's busy now. I'll just wait for some time, right? So I can wait persistently. That means I can go and check again. I can check again. I can check again. Or I can just basically say, okay, I'm going to flip a coin, or I'm going to basically pick a random number from, 1 to 32. And I'm going to say, okay, 18. I'm just going to wait for 18, in like 18 small time intervals, and each time interval could be like 10 microseconds. So I wait for 180 microseconds before I wake up again, and I say, hey, can I send a packet now? And I check again, right? Because I'm just trying to say, well, at some random point in the future, I may get a chance again, right? So now we want to implement this kind of politeness protocol, and also this protocol of saying, when do I check again? Because every time I check whether the channel is busy or not, I am consuming energy, right? So, and in fact, your phones and laptops are constantly consuming energy because they are receiving all these messages, which mostly are not for them, right? In fact, imagine that, imagine you get, like, you have, like, think of your email inbox, right? And your email inbox, suppose Penn had just one email inbox, all Penn students, right? They all check the same email inbox, and you can only read the messages. You can't delete any messages like that, right? So how would you go about checking for your email? Now that there are our Amy G, she would be getting like 1,000 emails a day. Our Dean Vijay Kumar, he would be getting 500 emails a day, and so on. And then you are just looking for, hey, where's Kate? Where's Kate? Oh, there are like 20 other Kates just in C's. Oh, where's me? Where's me? And they're like, oh, that message is for me. I mean, that's just crazy, right? And that's exactly what your phones are doing right now. They're just saying, hey, this is not for me. This is not for me. Not for me. Mostly it's not for you, right? I mean, it's kind of like a spam detector like that. So now let's go back to this polite protocol. And so with CSMA, it basically says, I can detect. Now this is basically time over here, and say B is transmitting. So this is the propagation time for this message to get across to A. And then it's sending a whole packet across after that time over here to A, right? Or it's sending that message across to D or to C like that, right? So, but now when it is transmitting this across space, it takes some time, right? And what is the propagation time? It's about 1 foot per nanosecond, right? So per nanosecond, electromagnetic waves can travel 1 foot like that. That's just a good rule of thumb kind of measure that you have. So this is actually very fast to propagate, but then for the message to actually be delivered, then it is taking time, because that's the channel, right? The channel means that you can't send faster than, say, 100 megabits per second. And so when you're transmitting across the channel, first you're detecting, okay, nobody else is talking at this time, then I can send. But what's the next problem? The next problem is that, what if B is trying to send a message and get started right there, and D does not know that B is sending a message, because D is clear at that point, and D checks at this time T1 and says, hey, nobody else is transmitting, and it transmits the same its own message at the same time. And very shortly after, the message basically overlaps with B's message, and either C nor A can receive that message, and it just gets garbled, right? So all these checkered points over here means that there's a collision, but D is not able to detect that collision, and B is also not able to detect that collision as a wireless node, because it can't listen and transmit at the same time. a wired node can do that, because a wired node can actually listen on the same line and transmit at the same time, because uh, on the wired network, this message that goes across globally to everybody. So this is kind of like a wired network kind of diagram, which is saying that, well, we are sending this message across, and then later on you detect, like, the message basically has got corrupted, but they continue to transmit because they can't detect each other. On a wired network, you can detect each other, and what you can do then is to say, hey, if I detect that you're going to transmit, then I just terminate the packet, and I terminate the packet earlier over here, and I say I'm not going to send anymore, and I'm going to stop transmitting in that time, right? But in a wireless network, I can't listen to the channel at the same time. In fact, your Ethernet protocol, it was invented by this person called Bob Metcalfe, who, as part of his master's thesis and then his PhD thesis, he actually invented the Ethernet protocol, the early version of that, where he was transmitting and then listening to the line and then detecting whether there is any communication, and that basically made him like a multimillionaire or billionaire, right? Bob Metcalfe. And so think about doing a PhD. It could make you quite well off, right? So let's see what happens over here, right? So we can't detect now any noise. So then with carrier sense, you can verify, the absence of any other traffic before transmitting. That's our politeness. But if a carrier is sensed, then the node basically waits for transmission to finish, and then it tries to initiate its own transmission. If two nodes send a frame at nearly the same time, then neither of them detect it. And so basically they still have a collision, but at a lower probability. So, and we still have this hidden terminal problem, right? That this hidden terminal like does not know the other terminal is talking to its receiver at the same time, right? So in wired networks, you could do something called carrier sense collision detect. And essentially I'll show you that pictorially over here. It's just saying that when B transmits and D transmits shortly after, and D is unaware that B is transmitting because the message hasn't reached D yet, then as soon as D detects that there is a transmission collision over here, then it basically aborts its transmission right away in the middle of the packet. It's supposed to send you 1,000 bytes, but after 300 bytes, it just says, there's a collision, and it just terminates that, right? It terminates the communication. So it doesn't waste all the time on the channel to send more garbled messages while it has detected that messages are getting garbled. But in wireless, you can't detect at the same time because you are broadcasting and you can't detect what is happening at the receiver side, and you can't detect whether you're receiving that, right? So now you need to think about what's the big difference between wired. Why can wired networks do this, but wireless networks can't do this, right? So you need to think about that a little bit. So because in wireless networks, you can't send and receive at the same time. And so now let's see what you can do, right? So in 802.11, which is our Wi-Fi standard, what it does is it says, okay, well, I need to figure out how to take care of this hidden terminal problem. And so first, obviously, I check if the channel is free, then I communicate, and that's called the carrier sense. I'm sensing what the carrier is. And if the carrier is busy, then I don't communicate. If the carrier is free, then I can communicate. And this is a way how multiple agents or multiple nodes can participate in a network, right? They just are more polite. But they also basically implemented this scheme called collision avoidance. So let's see what this collision avoidance means. It's just saying that before I talk to you, I send you a very short message, right? I'm not sending you 1,000 bytes of data. I'm just sending you like 30 bytes, a very small packet called a ready to send or a request to send. And then if you receive that small packet, then you say, hey, okay, here's a clear to send. You're clear to send, that's okay. And then I send you the data, and then you send me an acknowledgement back. So what does that effectively do? How does that take care of this hidden terminal problem, right? So it doesn't take care of like the collision problem that, if you are already in communication. But suppose if I send you what I'm trying to avoid is that we start communicating pairwise, right? So say between you and me, we are communicating, and just two parties are communicating, and nobody else should talk to you or nobody else should talk to me while we are communicating, right? So we want to basically inform the hidden terminal, right? So this transmitter is telling the receiver, hey, I want to talk to you. The receiver says, okay, it's clear to send, you can talk to me. But by the receiver sending a message back, the receiver over here, this is the transmitter, this is the receiver on this line. The receiver is sending a message back to the transmitter saying, you are clear to send, okay, it's a go. And the receiver is essentially also sending that message to all of its neighbors, including this hidden terminal, saying that, hey, I'm basically talking to transmitter T and for this amount of time. So don't talk to me. Don't try to attempt to talk to me right now, right? So basically what is happening here is that on every packet that is trying to get across the network is a competition for exclusive access of this wireless medium. And when we basically capture this wireless medium and have that exclusive access, then we need to inform all of our neighbors. The transmitter needs to inform its neighbors that, hey, I'm going to be talking to, for the next, 30 milliseconds to this node. And the receiver in turn needs to tell all of its neighbors and clear the air and just tell everyone, right? It's kind of like, you just start dating someone seriously and you tell the whole world now on, whatever Instagram or Facebook or whichever app you like to use, that now we are hooked up, we are serious, right? And that just means that you're taken and the other person is taken, and you're exclusive, right? But for some time in this case, right, because a packet is only for a short time, so the receiver, by sending this clear to send, is also letting the hidden terminal know that it is busy. So the hidden terminal now basically is exposed, is aware that there is some busyness on the channel on this side. So it takes care of this hidden terminal problem to some extent, like that, right? So so what is happening is that the transmitter is sending a message, request to send, and it is broadcasting that message. Since wireless is a broadcast medium, the signals are not just constrained in a wire or in the physical medium of the wire. And so it is telling all its neighbors, including this exposed terminal over here, that, look, I'm going to be using this channel for sending this packet and it's going to take so much time. And so till that time, nobody else talk, right? So it's kind of like you're talking to somebody and they say, hey, just hear me out. Let me finish my argument and then you can talk. So it's kind of like that, right? So similarly on the receive side, it informs its neighbors that it's busy and it's going to be in this conversation. And so this is kind of like clearing the air and just saying, okay, well, now we have got access to this by doing this four-way handshake of request to send or ready to send, clear to send, data, acknowledgement. We are able to then, we have kind of this exclusive access on that, right? Similarly, what is an RTOS trying to do is an RTOS is trying to give exclusive access of the processor to a particular task. So all of these are kind of, in the broad scheme of things, resource allocation problems. The resource in the RTOS case is the processor. The resource in this wireless case is basically the electromagnetic medium that we have, and so on, right? So in a way so what the node is trying to do is trying to lease the channel, and it's just, by lease is just saying that I want to book this channel till I finish the message, and it's going to take me so long to send this message across. So what that does is that when it sends an RTS, it also, as part of the packet, it has a thing called a network allocation vector. And a network allocation vector is nothing other than just saying that I need this channel for the next 140 microseconds. And then the clear to send says, okay, well, that packet took so long to send and for me to receive that. Now it's going to delete this amount of time and subtract that amount of time and say, oh, well, I'm going to clear to send and we are going to have this communication for this amount of time and going into the future. So nobody else talk to me till this time. Then the data is being sent across, acknowledgement comes across, and then acknowledgement basically says, this is the end of our relationship, because our relationship is only transactive in terms of one packet at a time. And now the channel is open for anybody else to compete or anybody else to transmit, like that, right? So this network allocation vector is a way of reserving the channel, but only for this duration and only after winning that exclusive access. So, but in order for an RTS to get across, it could have the same problem as another node is, is transmitting at the same time. They have a collision. The nice part is that the RTS packet is not as big as the data packet. It's only a fraction. Like it's about, say, 1/40 times the size of a data packet. It's really small. So if there's a collision, this collision is for a very short amount of time. So this is a way of trying to engineer, a protocol to bypass the problems of collisions in this shared broadcast medium. And we achieve that by carrier sense multiple access, listen before you talk. And then we also minimize the collisions by doing this collision avoidance over here. By collision avoidance, we're just sending, this four-way protocol that is clearing the space on the transmitter and receive side so that nobody else can collide with us after that for the duration of this time, right? So does that make sense so far? Any questions?
I'm a little confused about the network allocation vector. So that is like, is that like a predefined like set of time that if you receive like the ready to send, you just wait that time before you can before you start sending things again?
The network allocation vector is just saying that, I'm going to send you a request to send, I'm sending you the first part of the four-way handshake. And all I'm saying is that, I'm going to talk to you for the next, the next 15 minutes, right? So, so after that point, you can, so it's kind of like, your mom came to give you your lunch, right? So then you would basically tell her, okay, I'll come out afterwards for like some tea or something at 1:30. So you're just saying I'm busy for this duration of time. So the request to send is just saying that from now till an acknowledgement, this is the amount of time I want the channel for. Then we basically send the request to send, and the clear to send says, okay, now from now till the end of the time, this channel is mine. Okay, and then the time when this finishes, then it says, okay, the channel is free for all. So it's like kind of making a micro reservation like that, right? So it's in some modern terms of like, this micro reservation is just saying that because we all want exclusive access. And I think like people today are trying to get like these Amazon deliveries home, right? But you can't get Amazon deliveries for groceries, and it's really a big problem. I don't know. I don't do that delivery stuff, but then so they have to basically get a slot in the future now, right? So, but this is just making an instantaneous reservation, and it's just leasing the channel for that time. So, so all it is a counter. The network allocation vector is just a counter saying that for so many microseconds, I'm going to use this channel. It's belongs to this pair. Okay, so I'll use the last. I'll explain this packet formats, so you get an idea of how packets are actually now sent across. Because there's some little interesting parts, right? So there is this random backoff. Basically, it just says that every time I sense the channel, I want to basically check if the medium is busy for some time, and this is the amount of sensing time. And so that is all described as part of the protocol, right? And it's just saying, okay, I'm going to put my antenna on, and I'm just going to listen. I'm just going to be in this listening mode and say, okay, now the channel is free, and then I can basically send my data. If while I'm waiting and I'm listening and somebody starts talking and I say, oh, somebody's talking, channel is busy, then I basically just go back to sleep and I set a timer to wake up at some random time in the future. So who can tell me why we choose this random time in the future? Why can't we just pick like a fixed time in the future?
Is it because multiple might be encountering the busyness at once, and then if everybody comes back at a random time, they're less likely to collide again?
Yeah. So randomness in some sense also brings about some fairness, right? It's just saying if I have a uniform distribution, then you have an equal chance of getting access to this channel as much as I do. So it's kind of a fairness approach. Random, what this back off just means is that the channel is busy right now, and maybe more than one party also wants to access this channel. We don't know how many parties want to, but we're just going to disperse. And by dispersing is just saying that there's almost like they treat this, this channel being busy as some congestion, and it's saying I'm going to come back later. So like, for example, we know on a normal non-COVID, day, like say Friday afternoons, there's very busy traffic. So what do people do? They try to disperse. They say, oh, well, I'll go at like 10 in the night. Like, usually when I go to meet my family in New York, we just, drive at 10 o'clock in the night and reach there at midnight because there's no traffic at that time. But we basically went in a non-ideal time. So this randomness is basically just kind of spreading out when parties try to access that channel. So when you look at, so the protocol, like 802.11 is a protocol, it's a standard, and they have defined what this sensing period is, what is the maximum size of the data. So I want to just skip ahead to, so just before we close up this, so we know Aloha goes up to 18%. And then carrier sensing, by just detecting, should I send or not, that basically can raise the throughput up to about 60 to 70% of the available throughput that is there. And then carrier sense with some time division multiple access. That means it's also saying that we'll synchronize with nodes and make sure that at this time, you are available, I'm available. That can increase the throughput to about 80%. But 80% is like kind of the theoretical maximum that you can have there, right? So and so your Wi-Fi is something like this. And so what is this? X-axis is just saying more users you have, the throughput actually goes down. Who can tell me why the throughput goes down while I get some water? So why would the throughput go down? It's kind of like traffic congestion, right? I mean, if you go at 5 p.m. on a Friday and you're just in the middle of all the traffic, nobody can, it just slows down, right? So why does traffic slow down? Why can't they just drive fast and, all get across? Because the channel can only allow one exclusive, communication at a time, right? So now everybody's trying to fight for exclusive access. And then we're just fighting. And then it just says, no, you try later, you try. Every time you try, you basically got to get a back off over there and say, try again. And so that's sort of the, the problem, that this is actually congestion that is delaying this, and just means that all the users now, as we go to more users, not only is the throughput going down, it also means that the latency is going up exponentially because all of the users now have packets backlogged in their queue. Right. So then there are different protocols that are there and say, how should we access the channel? Right. So I want to skip ahead to how, how we basically go to a Wi-Fi frame. Right. So this is the protocol frame that the Wi-Fi packets use over here. And that's called the medium access control header. Right. So it's basically saying, OK, there's some frame control that's basically saying this is a, what type of a frame is this over here? So there are frames that are, frames that are just there for you to associate with the network, for you to leave the network, for you to synchronize with the network, to get authenticated. There are control frames that are like the ready to send or clear to send or acknowledgement. And then there are data frames, right? It's just saying, here's the data, that's it. So, but now suppose I'm sending a message now from, from me to somebody else that is across 5 hops in a network, and these hops could be wired or wireless. How do I get this message across, right? So we have essentially in this case we have 4 addresses, right? So one is the address of the source, and then there is the address of the destination, The third one is the address of the current transmitter. And the fourth one is the address of the receiver. So what is the difference between the source and the transmitter? It just means that suppose I have to go, you are 10 hops away from me and I'm transmitting. So then I need to say, hey, I want to send this message 10 hops down to me to node J. And if I want to get to node J, then it says, okay, B, you are the next hop, you are the next receiver. So in the beginning, I'm the transmitter and I'm the source. So A is the transmitter and A is the source and J is the destination and B is the next receiver. Then when B gets the packet, B says, oh, this packet is not for me. I need to forward this down the line. So B says, A is the source, I am the transmitter, B, and then C is the receiver, and then J is the destination. And so basically what is changing as the node is hopping through the network is the intermediate addresses of who the current transmitter is and who the current receiver is. But what is not changing is who is the source and who is the destination. So that's why we need 4 addresses to basically send a message across, like a mesh network. Okay, so does that make sense to you guys? That I can't just use 2 addresses because I need to know who the next person receives this message because I want to forward it in that direction. Like that, right? Now, I may not know spatially where everybody is, but I definitely know how to get from where I am closer to that destination. So now who determines what is closer? That's a routing protocol. We won't cover that here. It used to be part of the course, but we have to make the course a little bit simpler this semester. So we won't get into routing. There used to be a lab also on building a network and routing packets, across, 6 different, embed size nodes, but we don't have that lab now. But essentially the routing protocol is just saying, if you want to send a message from Philadelphia to Singapore, well, you need, like I showed you last time, you need to basically get to Philadelphia Central, from Philadelphia Central, get to New York, for example, from New York, get to the next point, right? So, and we saw how this message went to Switzerland directly from Philadelphia, but we saw the paths that it was taking, but that is a routing protocol. How do we get a message across? But this is a medium access protocol. It's just saying, how do I get the message across 1 hop at a time, right? So from each hop. So that's the packet header. And so this is the frame control is basically saying, what is this type of packet? This is the start of the packet. And the duration ID is basically saying how long is this packet, that is the network allocation vector. Sequence control is saying, well, I am packet number 17 out of 32 packets that are going across in this communication. The frame body here, you can see these are the number of bytes over here. So for each address, we have 6 bytes. So the 6 times 4 is 24 bytes is just for the 4 addresses. And then we have usually an Ethernet frame could have a maximum body of about 1500 bytes. But you got to keep into account that the longer the packet, the larger the probability of that packet getting into a collision, in the network. And then the CRC is basically the cyclic redundancy check. It's your checksum, about parity bits, but this is like a 4-byte, kind of complex parity bit. It's a polynomial based approach of doing, looking at message integrity. And so like here you have different address fields. There are 4 address fields, and that's pretty long, right? So for your MAC address for your laptop is 48 bits long, right? And every laptop has a network card, or that has a network card, has that is Ethernet based, has a 48-bit unique ID, right? And so like no other laptop in the world has the MAC address that my laptop has. And that's one way of uniquely identifying physically what is the hardware address of this laptop. Now, so then there are different address types, like I showed you the 4 address types that we have. And then there is this basic service set ID, right? This is the SSID that you're familiar with the Wi-Fi node network, and so on, right? So in Wi-Fi, you can communicate with, in a broadcast way, in a distributed way, like I just showed you with this CSMA-CA protocol. And you can also operate in what is called a point coordinated function, which is not used often in Wi-Fi, or not even provided. It's just saying that the access point can sort of schedule communication and say, now you go, now you go, now I go, now you go, now you go. And it can basically have a scheduled pattern, right? So when I was doing my master's thesis, I was working on these kind of protocols long time ago, and it was very interesting at that time. So the 802.11 standard has, many different packet types, and then that's a standard, right? Now it says, okay, well, we have all these different types of packets. These are the different ways you can communicate in a random access way or in a way that is, synchronized. And this is the kind of handshakes that we can have with RTS, CTS, and data and acknowledgement that takes care of the hidden terminal problem. The media reservation is done with a network allocation vector. It's half duplex, so you have to send an ACK back just to say that, okay, it's the end of the problem here. You can fragment a large byte. Suppose you're sending like a 1 megabyte file across, and then that will break it down into, say, 1500 byte packets, and it'll say, okay, well, I'm going to divide 1 megabyte into so many different packets. I am the 17th packet out of so many packets. To avoid collisions, it has a backoff, and it just senses the channel. If the channel is busy, it doesn't go and transmit. It basically backs off and waits for some random time, and it can have sleep and wake also. So that's the end of just Wi-Fi, just describing to you and giving you a high level understanding of how we took care of the hidden terminal problem and what does a packet look like, right, for Wi-Fi at a very basic level, right? So I'll stop here in terms of the lecture, but what questions do you guys have?
So going back to detecting collisions, to detect a collision, it's on the receiver side then, right? Like when you send a packet, they have to send back acknowledgement. And if there's no acknowledgement, then there must have been a collision.
That's true. That's true. So one way, so that is detecting a collision, right? So you in wireless, you only detect a collision by the absence of not receiving like an acknowledgement. But so detecting a collision is very inefficient because I need to be like, hello, can you hear me? And if if this is just a phone call, right, not a video call, then like say we're talking to Matt, right? And I say, hey, can you hear me? And then I don't see his face, so I don't get any signal back in that sense. But after, so or I ask you guys a question, and if nobody answers a question, then I say, okay, well, I'm going to keep a timeout of 30 seconds. But I have to waste that amount of time on the network to time out and then say, I think they didn't receive the packet. This is the point where I say I give up, and we need to try to see that, right? So that's very wasteful. So instead of waiting to detect or to basically time out and check whether collision happened or not, a more efficient way is to just avoid having a collision by doing this carrier sense collision avoidance, right? So and the first is carrier sense, be polite and detect from the transmitter side, put the antenna up, detect is the channel busy or not. And if the channel is busy, then don't send anything because we're going to have a collision, then we have to time out again and it'll just take too long. So don't preemptively waste the time. And the second is use a protocol that is now going to actually have a way to just send messages like this to clear the air, right? To clear the communication space with using this RTS, CTS. So both parties basically tell everybody, hey, I'm busy for this time, don't talk to me till this other time, right? So we are trying to avoid a collision from happening. So how do you detect a collision? You can detect the collision only at the receive side. And now the problem is that the receiver did not receive your packet. So the receiver has nothing to tell you, right? I mean, you can say, hey, I wanted an extension for, the current lab, but I didn't receive your message. And then I say, hey, I didn't receive your message. So I wasn't able to respond to it like that, right? So yeah, so. Okay, any other questions? So for your quiz, you will have the serial communication protocol, not much of this wireless stuff will be on your quiz, but you will also have a question from controls. Okay, and the controls lecture is online also, and we'll cover that on Thursday. But Chris will cover that in recitation tomorrow. So I highly recommend you go for the recitation or watch his video recitation, and also come for the Thursday lecture on the controls lecture. Okay, but you can watch the controls lecture, and that covers that. We're only going to ask you some basic control questions like that. You're not going to be answering some numerical problem. Okay, all good. Everything else is good. Okay, let's end over here. And then if you have any more questions, ask us on Piazza. All right, guys, have a good day then. Bye.